So we're going to use our notes or our ideas that we learned yesterday with graphing reciprocals. And here's the idea stated again. We're going to draw our original function first. So for cosecant, we're going to draw sine. When we do secant, we're going to draw cos. And we're going to do tangent, we're going to draw cotangent. And then we're going to go through the steps of looking for asymptotes, finding certain points and doing 1 over y for those points, getting the general shape and drawing the asymptotic behaviors, and going from there. So here is our graph of sine, and you have it at the bottom. First thing we do with reciprocals is look at our asymptotes. Are there going to be any vertical asymptotes? Wherever sine is equal to 0. So here, here, and there's going to be, on this graph, quite a few of them. And in this direction. So there's our vertical asymptotes. And you can imagine if you kept on going, there would be an infinite amount of them. Now, will there be a horizontal asymptote at y equals 0? We drew that whenever our graph either went up forever or down forever. But can you see that your sine graph stays between -1 and 1? So there's going to be no horizontal asymptote for this graph. Now, when we start looking at values that we know, can you see that you know this value right here? At pi over 2, comma 1. What's going to happen to that point? It's going to stay, pi over 2, comma 1 is going to stay the same. Because we remember that any place where your y value is 1, when you do 1 over 1, it's going to stay the same. So in fact, all of these maximum points are going to stay the same. Does it make sense that all of those minimum points where y is -1, those are all going to stay the same as well? Think of your pi plate. What's another point that you know on our original graph here? We know 2 pi, that's 0, but we've already got an asymptote there. What's another point on your pi plate that's not equal to 0 or 1 that you know? Well, that wasn't a hand. What do I get right here? Pi over 6. What happens when you plug in pi over 6 for sine? Sine of pi over 6? 1/2. So that's a point on my original graph. What's going to happen when I do the reciprocal for that? I'm going to get pi over 6, comma, and if I flip 1/2, I get 2 over 1, or just 2. And with reciprocals, one thing that you might notice, as one of your functions gets closer to 0, your other function gets bigger and bigger and bigger. So in this section, it's going to look like this. And since this section's the same, we're going to have a similar result there, a similar result there. Yeah, one point is going to be nice. At 1, if you wanted to graph this other point at pi over 6, comma 2, to show that you understand, since I know that pi over 6, comma 1/2 is on there, I can do the reciprocal of that. Similarly, all these places that are negative are going to show your asymptotic behavior And our blue graph right here is the graph of cosecant of x. So we draw our sine graph first, and then we can do the reciprocal from there. Yes? How do you represent cosecant on the circle? I'll show you that in a second. Okay? I'd like you guys to try secant. Yes, Jessica. And since the shape of cosecant is, since the shape of cos is the same as the shape of sine, the shape of secant is going to be the same shape as cosecant was. So these points are going to stay the same. Then it's going to go towards your asymptotes. And if we think about a point that we know on our unit circle, we know that cos of pi over 3 is a half. So you would know that secant of pi over 3 is 2 over 1. So even though there's no asymptote at y equals 0, our graph still can't equal 0. Because anytime you have a function which is a fraction like this, the only way a fraction equals 0 is when the top of your fraction or your numerator is equal to 0. But our numerator is always 1. So we're not going to have any place where this is equal to 0. We don't draw the asymptote because the graph doesn't approach it. So an asymptote is not needed. But it does tell us that we need to go down in these areas rather than up. But you can see that with a single point as well. Someone had asked, where do these things show up on the unit circle? So here I'm going to look at sine and cosecant. Got a little unit circle drawn here. We know that sine is the y coordinate. So on my unit circle here, I've got that drawn as a blue line. And it's a little bit hard to see because of the colors. But if you would draw a tangent line at that point on the unit circle, the length from here to here is cosecant, which is drawn in a brown line. So as I drag this point, as sine gets closer to 0, that tangent goes higher and higher, and that's the length, that vertical length on my y-axis is cosecant. As I go down over here, cosecant goes back up, down over here, and you can see the graph as you go around. Now your x-coordinate is cos. So if we want to look at what happens, there's secant, I'll put cos on there. Your secant line is along the x-axis now, wherever the tangent line hits. That looks kind of pretty. And now we're going to look at cotangent. So there's our graph of tangent. And wherever tangent is equal to 0, we're going to draw our asymptotes. Cotangent acts a little bit strange. Let's draw our asymptotes here. Wow. There's our asymptotes. They happen at all of our multiples of pi. Now cotangent is 1 over tan, and cotangent is also cos over sine. Now in the graph of cotangent, it's going to make a difference if the graph of cotangent is to be decided, should we graph 1 over tan or should we graph cos over sine? Because it's going to be a little bit different. Because if I graph 1 over tan, you can see that my original graph goes up forever and down forever. And so according to our reciprocal graph rules, we would have an asymptote at y equals 0. There would be a horizontal asymptote. Everything that we see in this graph says we should have a horizontal asymptote because this fraction right here is never equal to 0. However, if we consider this fraction, cos over sine, is cos ever equal to 0? Yes. When does cos equal 0? It equals 0 at all the odd multiples of pi over 2. So instead of having an asymptote at y equals 0, we do graph cotangent as if it were cos over sine and not 1 over tan. And we do include those points. Now we know that tan of pi over 4 is 1. And when we do the reciprocal of that, we would get 1 as well. Yes?
Why do we graph just cos over sine if we graph all the other ones as 1 over itself?
Well, we're still going to use the idea as 1 over tan for graphing because it's easiest to take it from because we don't know how to graph cos divided by sine. But we just use the cos over sine to say instead of an asymptote being at y equals 0, there's an actual point there. So it's just a small little detail. Everything else happens to be the same idea as graphing 1 over tan. We're going to make wherever the y values on tan are 1, that point won't change, an invariant point. Same thing at -1. Wherever our y values are -1, those points won't change. And we still got our asymptotes from our tan graph. Once you've got your values of 1 and -1 and you include 0 where those asymptotes were, then your cotangent graph is very similar to your tangent graph. Yeah, once you put everything on, especially if you're using the same color all the way through, gets a little busy. That's why when we did our notes the other day, sometimes we did one graph where we drew our original graph on one side and our reciprocal graph on a new one just so that it wouldn't look busy. But for these ones, we are drawing them on top. So now what we're going to do is we're going to go back through each of these and characterize them. We're going to say what the domain and the range is, list our y-intercepts if there are any, list our zeros if there are any, list the period if it has a period, and we'll talk about whether something is odd or even. Here's our cosecant graph. So you have space at the bottom there. We're going to do our domain, our range. Say if we have a y-intercept and all of our x-intercepts. What was the other things we're going to characterize? The period. and whether something is odd or even, and I'll tell you what that means in a second. The domain of sine was everything, but when I have 1 over sine, sometimes I'd be dividing by 0. And that's wherever we have our asymptotes. Right, equations of asymptotes was another thing. Now, our equation of our asymptotes is going to be very related to our domain. Can you see that our domain is everything, but x can't equal pi, 2 pi, 3 pi, 4 pi, 5 pi? How am I going to say all of those all at once? X can't equal k pi, where k is an integer. For our range, y is less than or equal to -1, or y is bigger than or equal to 1. Could also write this in interval notation if you would like. Now, our equations of all of our asymptotes will be x equals k pi, where k is an integer. Whereas before, for our domain, we would say x can't equal k pi. For our equations of our asymptotes, anytime you're writing an equation of an asymptote, make sure you look at your notes. Make sure you didn't put a line through there to say x can't equal, because it is an equation, and every time you have an equation, you have x equals. So the equation of that asymptote is x equals pi. When we write it as a domain, we say it can't equal. When we write it as an equation of an asymptote, we say it does equal. Do we have any y-intercepts? No, because there's an asymptote there. Do we have any x-intercepts? No. Over what period of time, over what length does this repeat itself? Can you see, if I go back up to here and I take out my highlighter, it doesn't repeat itself just over that, because we also have this section down here. But that yellow part repeats itself over and over and over again. How long is it from here to here? Our period is 2 pi, which is the same as the period that sine was originally. Yes?
You know those like transformations of the sine cos graphs?
Yeah.
We have to do transformations of the reciprocals.
Sometimes there are simple ones which have like just moving it left or right, or just moving it up and down.
Okay.
But usually not as complex as ones that have all 4 transformations like we do with sine cos.
That would be a little tricky.
Yeah. Now, sine is an odd function and cosecant is an odd function. The definition of an odd function is if you reflect it over both axes, you end up with your original graph. So I'm going to take out a purple pen here. I'm going to say if I took this part here and I reflected it over the y-axis, can you see that it would end up over here? And then if I reflected it down, it would end up right there. If I would flip it over both axes, and in fact, if I take this whole right-hand side, flip it over, and then flip it down, it's going to match up perfectly. That's the definition of an odd function. Can you see that that happens with sine as well? If you take your sine graph, and I take that graph and first flip it over this way, and then I flip it down, it matches up perfectly. That's the definition of an odd function. The the way that you write that definition in function notation, you can either write it this way. What I was doing is I moved that negative over here, which says that negative outside, that affects your y values. That's going to flip it down. Negative inside your function, that affects your x values. That's going to flip it over the y-axis. And both of those flips equal the same function that you begin with. Yes? That's right. The asymptotes are always at the original graph's x-intercepts, because remember what the reciprocal does is it changes every y value to 1 over y. And all of these points that were originally x-intercepts, all of those points are where y would be 0. And when you do 1 over 0, that's not allowed. So that's why we get those vertical asymptotes. For a secant graph, domain, range, and our asymptotes, x-intercepts, y-intercept, our period, and whether it's odd or even. So our domain, x can't equal, and we've done this already when we were looking at sine and cos graphs. When we were looking at our cos graph and we had to list all of the zeros, we did it in one of two ways. We could start with one that we know. So let's say I start with pi over 2 because I know that that's one of my non-permissible values. And then we notice that the distance between each of my asymptotes is exactly pi. So x can't equal pi over 2 plus k pi, where k is an integer. We'll count all of those asymptotes, because you can subtract pi as many times as you want or add pi as many times as you want. The other way that we sometimes wrote the domain, I'll write it down here. We notice that all of my pi over 2's are odd numbers. So x can't equal an odd number times pi over 2. Now, it's not mathematically correct to write the word odd in here. We still need to use a k. The way that we show an odd number is we take any integer and multiply it by 2. That makes an even number. Then if you add 1 to any even number or subtract 1, you get an odd number. So this will say an odd number times pi over 2 when k is an integer. So if you were asked to write down all of the asymptotes for one of these graphs, or write down the domain, for secant or cosecant, you could write it this way for secant, pi over 2 plus k pi, or you could write it like this, 2k plus 1 over pi over 2. If you actually multiply this out, you'll notice they are exactly the same. But just two different ways of thinking about it, and whatever makes the most sense for you for writing it. The range is exactly the same. Y is less than or equal to negative 1, or y is bigger than or equal to 1. Our asymptotes, again, you can choose either one of those. And again, there are no x-intercepts. And this time we do have a y-intercept at 1. Just like our cosecant graph, our period is 2 pi. And this function is even. So what makes an even function is if you would take the graph and just flip it over the y-axis. So if I would take this part of my graph and flip it over my y-axis. You see it matches up perfectly because my drawing was so good to begin with. So the definition of an even function is that flipping over your y-axis, if that graph matches up exactly as you began with, then it is an even function. So for example, here's my cos graph. If I take that cos graph and I flip it over top, right over the y-axis, it matches up perfectly. So cos is an even function as well. Twice. Yeah, so if I take this yellow, flip it over, it doesn't match up, but if I flip it down, it will match up. So a double flip for odd and a single flip for even. And the reason they're called even and odd is because if you look at a parabola which has an even exponent, it's an even function. And if you look at an x to the cube graph which has an odd, if you flip this one twice, it matches up to what you start with. In fact, that works for any polynomial. A plane x to the fourth graph is even. A plane x to the fifth graph is odd. Finally, our last one, cotangent. Our domain for cotangent is exactly the same as our domain for cosecant. X can't equal k pi. That's because we have asymptotes at every multiple of pi. Our range is everything. Our x-intercepts are the same places where cos is equal to 0. So our x-intercepts are all starting at pi over 2 plus k pi, where k is an integer. Again, you could write it as the 2k plus 1 times pi over 2 as well, where k is an integer. We have no y-intercepts. And how long does it take for the cotangent graph to repeat itself? Can you see that it repeats itself from 0 to pi? So that means its period is pi. And that's the same thing for tangent, right? The period of tangent is pi. The period of cotangent is pi. Can you see that if you did a double reflection, it would match up? So this is an odd function.